method is heat mechanic coupling. We'll go into the prerequisites and then, as usual, first tackle the governing equations we need for such problems, which are heat conduction, solid mechanics, obviously, and then we will need to include thermal strain into our Hooke's law, and also quickly discuss the phenomenon of on strain heating, which we will later neglect in the coupling. And with this assumption, we can derive our finite element formulation. And then I'll give a few tips and important points you have to consider when you model heat mechanical coupling. Okay, so let's start right into it. Of course, we need heat conduction and we need solid mechanics to model thermal expansion. So in solid mechanics, we need to adapt our Hooke's law to include thermal strain. So just to recapitulate, we have the heat equation where the solution variable is the temperature T, and we can solve it via the finite element method to obtain the temperature distribution in a solid body. And if we have that, we also want to consider the mechanic problem, and this is in general the governing equation is the balance of momentum and a constitutive relation that describes our stress tensor sigma. And from this problem, we will finally compute the displacement field U in our solid body. So let's look at the phenomenon of thermal strain. We know that a change of the temperature T, so we denote the temperature change by delta T, will lead to a thermal strain. And this thermal strain, denoted here by S thermal, so this is again a strain tensor, is related or can be described in the simplest manner by a thermal expansion tensor alpha thermal times the change in temperature delta T. And usually the change in temperature is given by some reference temperature that we know, which is strain free, and the current temperature T. So this difference drives our thermal strain. And the thermal expansion tensor, alpha thermal, has to be of the same rank as the strain tensor, since it relates a scalar temperature change to a tensorial strain quantity. So in general, the thermal expansion tensor is of rank 2, like the stresses and strains we have. And very often, so it has 3 components in the diagonal, has to be some symmetric, and it has 3 off-diagonal terms describing the shear strains, and the normal strains are, of course, in the diagonal. Very often, however, we take the assumption of isotropic thermal expansion. Of course, this is most likely only true for isotropic materials like most metals, for example. And then we only need a single parameter, which will be then in the diagonal of the thermal strain tensor, and all the shear components are 0. So let's formulate Hooke's law, including thermal strain. So first of all, we have to know that the elastic strain is the total strain subtracted by the thermal strain. So now we are a bit more precise in our notation. SE is our elastic strain, and S, as we had it before, was the total strain. So therefore, we can write Hooke's law in these 2 forms, either formulating the elastic strain using the inverse of the stiffness tensor, double contracted with our stress tensor sigma. And of course, you can shift this around by multiplying the stiffness tensor to the other side by using the inverse. So we have the usual form of Hooke's law, sigma equals C double contracted in S elastic. And now we have refined the notation, since Hooke's law has to be formulated for the elastic strain. And of course, we can now insert our relation for the elastic strain, which then gives us Hooke's law, including thermal strain. In the formulation, we needed equation 24 for our finite element formulation, because you remember in the balance of momentum, we have the stress tensor, which we need to insert using the constitutive relation, which is now our extended Hooke's law, including thermal strain. Another phenomenon that has to be discussed when modeling thermal extension is the phenomenon of strain heating. So if an elastic body undergoes deformation, we know that heat is generated. You can see this when, for example, rubber dampers are heated up during operation. And this phenomenon can be described in the simplest case for a temperature constant thermal expansion tensor by this relation. So the power dissipation is approximately the thermal extension, the thermal expansion tensor times the absolute temperature of the body double contracted with the stress rate with which the body is deformed. And from this relation, you can see that this is only a significant portion of heat if the absolute temperatures are high, so if the T is high, or we have very fast stress variations, so the time derivative of the stress tensor gets large. So if we excite, for example, a rubber material at a very high frequency, we know we need to take this term into account. However, if we simply lower the frequency, we know it won't get heated a lot, and we can neglect the phenomenon of strain heating. So this relation would be a source term for the heat conduction problem. And in this way, the problems would be tightly coupled, since the mechanic sub-problem leads to a source term in the thermal sub-problem, which in turn will change the temperature, changing the source term again. So if we can, however, neglect strain heating, so we don't have a high absolute temperature and we know we don't have very high stress rates, we can neglect this source term, and then the mechanic field has no influence on the thermal field. And this is a very useful assumption for many application problems, and therefore it is considered in the following. So in this case, we have a forward coupling. What does this forward coupling mean? This means basically the temperature distribution causes thermal strain, and then we assume the mechanic field has no influence on the heat conduction problem. Like, for example, we have a static problem, so no time derivative, or we can neglect the strain heating effect. And then this coupling becomes a one-way coupling from the temperature field to the mechanic displacement field. So the analysis approach is simply we compute the temperature distribution and then apply thermal strain and compute the mechanical displacement field resulting from the given temperature distribution. And how this works, we'll look at now. So we want to derive the finite element formulation. We're not going to do this in detail since it's very straightforward. So you start from the balance of momentum in the usual procedure. So you do the integration by parts and you insert your boundary condition and you insert your Hooke's law now, including thermal strain. And what then results is the following weak form, where we have the stiffness term that we had usually. We have, of course, the mass term also. and we have our boundary terms, they are unchanged. What, however, changes is now we have an additional term on the right-hand side where we know the temperature change, delta T, and we know the thermal expansion coefficient. So this is a known term, which will be assembled on the right-hand side. So this is a kind of forcing term in the sense of a volume load, since we have to compute a volume integral. And that was basically it. Then the finite element procedure is used to obtain an algebraic system, which we can solve in the usual manner. So let's look into what additional post-processing results we will get. We will get the stress, of course. This is the actual stress in the structure. So we have to be careful that we subtract the effect of the thermal strains. We have, of course, the strain. So this is the actual strain given by the usual relation that we have assumed for small strains. And we have the thermal strain, which is alpha thermal times delta T. So this is the source term we have assumed on the right-hand side. However, since the alpha might be anisotropic, this is not strictly obvious how the thermal strain looks like. So you can basically visualize it as a post-processing result. And we have the thermal stress, which is simply the thermal strain scaled by our stiffness tensor. Then we have to, for modeling thermal expansion, we have to take a few assumptions. And one is the stress-free configuration. This is in general unknown. So be aware that you assume that the machine part, for example, you're analyzing, you simply assume it's in a stress-free configuration. In the configuration, you have the CAD file in, for example. This does not necessarily have to be true. This is an assumption. You should be aware of this. And the same holds for the associated reference temperature. So you usually set, say at room temperature, I think my part is stress-free. However, that does not have to be true. For example, due to production processes, there might be internal stresses in the part already. So in order that this assumption is valid, the error done by this assumption must be small compared to other effects you're investigating. For example, the external loading on the part you're considering. And this is often the case, but does not have to be true. So be aware of these assumptions you're taking. The other thing we have to consider is thermal stresses. This is what we want to compute, and they arise depending on the specified boundary conditions in the mechanic problem, of course. And so just think about a little bit what could happen to a body that is expanding under thermal load or under temperature change. So unconstrained structures may remain stress-free under temperature load if it's uniform, for example. But this does not have to be the case. If you have a temperature gradient in your structure, that usually results in the change of configuration and also internal stresses. And also consider that you can have significant stresses arising due to temperature loading. For example, metals may even yield at the temperature difference of about 150 Kelvin, given the correct or given boundary conditions that introduce high thermal stresses. And when will this usually happen? For example, let's look at the typical modeling era. Let's consider we do a mechanical stress analysis of a typical part, and what you often do is you say, okay, we have zero displacement boundary conditions at some supports, which, however, in reality is elastic. So if you combine that with introducing a thermal expansion of the part, this will quite often lead to a very large overestimated of the stresses in the part, because you actually constrained it using a fixed support, where in reality it's elastic. So be careful when specifying boundary conditions in thermal expansion analysis, not to over constrain your structure, because the boundary conditions you assume have to reflect reality. Finally, let's look at the temperature units. The used temperature units are in principle arbitrary, like any unit system. However, they must be consistent with the rest of the material definitions and boundary conditions. If you do the thermal analysis, typically only the gradients are important. So you may shift the solution to arbitrary temperature values. For the thermal stresses, we need the temperature difference to some reference, and this reference you have to give, and this reference has to be appropriate with respect to the absolute temperature you obtain from your heat conduction analysis. And finally, Kelvin and degrees Celsius can usually be used interchangeably, for example, for the thermal conductivity. So if it's per Kelvin or per degree Celsius, doesn't matter in this case. A final remark, since you do two analyses and you couple them in a forward coupling manner, you have to exchange data from one analysis to the next. So in principle, the thermal and mechanical field could be computed on different grids. For the sake of simplicity, we usually don't do this, since if you compute them on different grids, you have to interpolate the thermal field to the mechanic field in order to be able to evaluate the temperature at every integration point of the mechanic analysis. So typically we use the same grid